problems of quantum mechanics. Okay, that is okay. What we said is, yeah, here kada, last point. Okay, why the angular momentum of an electron in an orbit is an integral multiple of h by 2 pi? Why is the angular momentum an integral multiple of h by 2 pi? What do you mean by that? That is, according to Bohr, angular momentum P is mv, mass into velocity, right? mvr is equal to nh cap or nh by 2 pi. nh by 2 pi. That is what Bohr said. Now, why is it so? Why is it so? He could not say anything. He could not say anything. But after de Broglie's proposition, it's so simple to see. How is it simple, sir? Nothing. Okay. This is multiply this 2p to that side and bring p to the other side. So what do we have? 2 pi r is equal to nh by p. What is this 2 pi r? This is the circumference of the circle with radius r. 2 pi r is the circumference of the circle with radius r. Okay, what is n h by 2 pi? N is an integer. Okay, keep it aside. H by p. H by p actually gives h by p actually gives the de Broglie wavelength. H by p gives the de Broglie wavelength. Okay, from this, what it could be said is, okay, because h by p is lambda de Broglie, okay, h by p is equal to lambda de Broglie, this 2 pi r is equal to n lambda de Broglie. That is, that is the circumference of a circumference of the okay, circle 2 pi r is equal to n into lambda de Broglie. Sir, what is this circumference doing here? This is your Bohr's, okay, circles, or to say Bohr's radius r. R is the Bohr's radius. Okay, so this is the circumference on which the electron is supposed to be moving. This is the circumference on which the electron is to be supposed to be moving. And when electron is moving in this circumference, then it has to be equal to n into lambda de Broglie, where lambda de Broglie is the wavelength associated with that particular electron. Sir, you have equated mathematically very good, but what does it actually say? We don't understand anything. That is expressed here in this figure. Okay. Now I'll give you, okay, 10 seconds to observe the figure and tell me something which you have understood here. Okay. Your time starts now.
Motion of the
Yeah. Did anybody observe anything?
it's the motion of
Yeah.
electron.
True. Who is it? Please
Electron
mention your name and
means
talk so that everybody can understand.
My name is Pranati, sir.
Yama Pranati.
Um, I think it's the motion of an electron, sir.
Yeah. But where is the electron?
It's moving.
in an orbit.
Okay. Right. Okay. So what is this left corner top figure is saying is, okay, when n is equal to 1, you say that you have a circular orbit, okay, and when you have an electron in it, okay, it will be revolving around in that particular orbit. Okay, this okay, this thick line is your orbit. And what is this dotted line? Okay, this dotted line is not really understood here. Okay, is not really understood here. Okay, now n is equal to 1. It does not seem to be understood anything. Okay, ఇంకొక circle పై లాగినట్టుంది అంతే. Okay, let us keep it. I'll come back to it, but okay, keep it aside. Come to this case. Okay, top right corner. N is equal to 2. Okay, that means okay, what is the n is equal to 2? Okay, please remember I am saying 2 pi r is equal to n lambda. N is equal to 1, 2, 3, 4, and so on, right? Okay, so here this one is 2 pi r, okay, is equal to 1 lambda. 2 pi r is equal to 1 lambda. ఏంటి సార్ lambda ఎక్కడుంది సార్? I'll tell you. And what is this? 2 pi r is equal to 2 lambda. ఇక్కడ lambda ఎక్కడుంది సార్? Again I'll tell you, wait. Okay, and then come to this case. Okay, this is n is equal to 3. That is 2 pi r is equal to 3 lambda. Okay, now this is your 2 pi r. The circumference is 2 pi r. And where are this? Okay, 3 lambda. Now let us start here. This is 1 lambda. This is second lambda. And this is your third lambda. All right. Okay, please do not accept. Please do not accept. Okay. Do you see 3 lambda here? Okay.
No.
What you have is 3 lambda wave is there, and you have, okay, encircled that wave over this 2 pi r wavelength. 2 pi r circumference. Okay. Let me say I'm starting at this center. Okay. Top center. Okay. Okay. From here to here, we have one wave, and here we have second wave, and here we have third wave. Nothing. You cut it here and extend this side and extend this side. You will get waves. Right? Am I right or not? Okay, what you can do
Yes.
is, okay, you can cut it here, okay, and extend the circumference on either side. So what you get is you will have waves running over a line. Okay, extend, cut this circle and convert it into a straight line. When you convert into a straight line, these things, okay, will be acting. These things, okay, these things will be acting like a waves. Okay, you not acting. Okay, you will see them as complete waves. Okay, so this is how, okay, this is 3 lambda, okay, of, okay, that is 2 pi r is equal to 3 lambda. This is 2 pi r is equal to 3 lambda. Okay, and when I go to this case, you can start it here, okay, increasing and then decreasing. This is 1 lambda, again increasing and then decreasing. Okay, or you can start it here, okay, increased and then decreased, and then again increased, then decreased. So you have two wavelengths here. You have two wavelengths here. Okay, now in this case it increased and decreased, so you got only one wavelength here. So lambda d Broglie, okay, here is as such equivalent to 2 pi r. Here 2 lambda d Broglie is equal to 2 pi r, and here 3 lambda d Broglie is equal to 2 pi r, and here 4, okay, lambda d Broglie is equal to, okay, 2 pi r. Okay, these are the figures, okay, are submerged in one another. Okay, now same thing, okay, 3, 4, 5. Okay, okay, I mean, n is equal to 3, n is equal to 4, n is equal to 5. Now what are these red things? If 2 pi r is not an integral multiple of lambda, if 2 pi r is not an integral multiple of lambda, okay, you will have this kind of, okay, disjunction. That means, okay, you will not have convergence. That means they will not be equal. What if they are not equal? If they are not equal, that implies this kind of electron motion does not exist. Why it does not exist, sir? Because in this case, the electron may lose energy. How can you say that, sir? Because in all these other cases, okay, these are acting like stationary waves. These are acting like stationary waves. That means the wave that got generated over here moves and again moves and again moves. That means they are in perfect phase. Because they are in perfect phase, they will be acting like stationary waves, and in stationary waves, energy is conserved. Okay, in this case they are not stationary. That means, okay, they will not have phase relation. Because they don't have phase relation, the energy is not conserved. So these, okay, this kind of non-integral multiple of n lambda, okay, non-integral multiple of n lambda electrons do not exist. Okay, that is being explained from this particular figure. Okay, electron in different orbit and orbital angular momentum, okay, is being expressed. Okay, so this is how, okay, why this is how, okay, it explains why, okay, 2 pi r should be equivalent to n lambda. Only when 2 pi r is equal to n lambda, you will have, okay, stationary waves, or to say, okay, energy conservation existing there. Okay, that is why all the electrons which are existing in one particular orbit do not lose or gain energy, because they will be acting like stationary waves, okay, around the nucleus. Okay, that's what is the beautiful explanation that is given from de Broglie's uh, to the Bohr's proposition that 2 pi r is equal to n lambda. Okay, that's the point here. So de Broglie wavelength. Okay, okay. What we have seen today is, okay, de Broglie hypothesis that nature loves symmetry, so it should okay, it should so matter also should exhibit wave nature. Second point is, if wave, okay, matter is exhibiting wave nature, then it should have a wavelength, and the wavelength is derived from Planck's law and Einstein's equation, that is lambda is equal to h by p. Very good. Is there any use of it? Yeah, immediately that is applied to Bohr's explanation. That is, Bohr said that 2 pi r is equal to n lambda. And why is it so? Why should it be n lambda? Because the electron exhibits wave nature, and when it is exhibiting wave nature, okay, when 2 pi r is equal to n lambda, we will get stationary waves. That means energy is conserved. So the electron will have a constant energy when it is revolving around in one particular orbit. That is explained from this part. Okay, what happens if it is not n lambda? When it is not n lambda, then constructive, okay, there may be some destructive overlapping may taking place, so the energies may be lost for the electron. So that is not possible. Okay, these are the three things that we have learned till now. And next, another important point is we are saying that matter exhibits wave nature. Matter exhibits wave nature. When I say that matter exhibits